Okay, so what I thought we can do is, I really wanted to do verification, and it does not look like we have enough time. So what I'm going to do now is I'm going to tell you about self-testing. Okay. And then I'll complete the thing that we were doing with the BQP equals QMA, yet PRUs exist. So I'll try to complete this in this lecture and the next, hopefully. This is like one of the building blocks for doing verification. And if you're able to finish this and make enough progress, then we can have one last lecture, which we'll start verification. And then afterwards, I'll just post a few lectures online for you to look at later beyond the course. So at least we have covered verification. Otherwise, I would feel really bad because that's one of the most important results in the field, and I kind of messed up the pace of the course. So. Okay, so I'm going to start with this. So suppose we're looking at this state. Okay, so suppose we're looking at 5 plus, which is just the EPR state, right? 0, 0 plus 1, 1. And the setup is the usual non-local setup, right? So there's Alice and Bob. You've seen this many times now. Also in your assignments, right? So Alice gets X, Bob gets Y. They have to produce A, B. Okay. But what we're going to do is, for this particular lecture, we're going to take X and Y to be 0, 1. And we'll take AB to be plus minus. Okay, that's just because the correlations are a little bit easier to write in what we're going to do now. Okay, and suppose that the measurement that Alice performs is given by the following. So A sub X is M plus X minus M minus X, and B sub Y is Bob's measurement, so that is given by N plus Y minus N minus Y. Okay, these guys are projectors. Okay, so given the question X, the projector is for the outcome minus, given the input X projectors and plus, right? So nothing very deep yet. Okay. And then we have some very simple observations. So we have that AX dagger is AX, and AX square is identity. Okay, similarly BX, so BX dagger is BX, BX square is identity. Okay, so far we've not done anything very novel. We're just setting up what the problem looks like. That's the equation number 20. I've actually forgot the. Okay, I'll send you what paper I'm looking at. I forgot I didn't print the whole thing because we're just doing a small part, and I didn't print the title, so I don't remember. Alright, so that's the first note. And now suppose that the shared state between Alice and Bob is AB, and we also had a P. Okay. So in general, the state doesn't have to be pure, but we're adding a purification register. For the purposes of this lecture, we'll just assume the state is pure. Okay, but in general, you can always make it pure by adding this environment, and even if you restrict the measurements to AB, everything sort of goes through. So, all right, and okay, so let this be the state shared between Alice and Bob. Okay, and then the notation is that PAB given XY is going to denote, as usual, the probability of getting AB given XY, right? So probability of Alice and Bob getting AB given XY were asked, right? So far there's nothing new. This all you've seen. You've also seen that it's local by definition, right? So it's local if PABXY, right? This can be written as what? As just a. You've done an assignment on this. I don't really think this should be very difficult. Pi lambda P A X lambda P B B Y lambda. Right. So far this is everything, you already know all of this. Okay, so now we're going to go a little bit beyond this. So we're going to define what is called a correlation vector. Okay, it's not quite a formal word, I'm just using it for convenience here, and it's this object. Okay, so it's just a sequence of numbers which is indexing all the different outcome probabilities given the various inputs. Okay, so you just basically vectorize this object. Okay, and if you do this and you plot it on a sufficiently high dimensional space, you're going to get okay, you'll get a set. So the set of p's, you can plot it and it will form a convex set, right? Because these are probabilities, so you can add them and take convex combination, they'll still be a probability. And the nice thing here is illustrated as illustrated. Okay, so what is the illustration? So the nice thing is that it looks something like this. Okay, in a high dimensional space, the classical, so the local correlations, so the local set, local meaning in this sense, okay, when you plot it, it's going to be like these facets, okay, with some vertices, and then the quantum set is also going to be convex, but it's going to be slightly larger, right, because of course you can realize a few more things. So this has this curved thingy, okay, and the facets of the local polytope are what are Bell inequalities basically. Okay, so it's a nice geometric picture to sort of keep in mind, although we'll not really use it much, but just to have a. I think people have done numerics and things, so you can sort of check. Yeah, yeah, it's a high dimensional thing because like already for two inputs, two outputs, you have whatever 2 to the 4, right? Oh, facet is like a face, but I guess in a higher dimension they call it a facet. So it's it's just an English word, I think, or a slightly modified technical word now. Is that okay? And this is what you can do with quantum mechanics. Okay, and then there's also the no signaling, which is also a polytope, but we're not going. The maximal violation would be like by this object, right, somehow. The vertices are where they actually coincide, right, the quantum and classes, so you will not actually have a violation. To get a violation, you sort of have to okay, but I'm not going to the geometry, like you can formalize it properly, but this just to keep in mind because you guys are smart and you'll read these at some point, so it's good to have some idea. And the way we're going to define the Bell inequality for us in this setup, so this is slightly different from how we were doing it for games. All this is the same idea. The difference is in terms of normalization. So we're writing it as follows. So A1, B1. So they all have the same sign except when both are 1, which is very similar to this, sorry. X dot Y was AX or B, right? Remember this was sort of the Bell predicate, right? So it was when the inputs are both 1, then you want something else to happen, otherwise you want things to work. So that's what it's sort of capturing, that when the inputs are 1, you have a different sign, so you want the behavior to be different, otherwise you want it to be the same. And okay, and then the inequality is that this should be, for local things, it should be at most 2. And this was a question, right, in your assignments, that for Cyrilson you can show this is 2, 2. Right, so this you've actually worked out, and this object, remember, is we defined it quite generally, right? We said whatever strategy you're following, I can write it as in terms of these observables, and so therefore, and these objects are then defined as follows, because we are defining it at the level of just probabilities. So we define it as A dot B, and then the probability of getting AB given XY, right? So okay. Okay, and then we also recall that the way we saturated this, okay, so this can be saturated by, so the 5+ state that we wrote over there, which is just the maximally entangled state, the simplest maximally entangled state, and then A0 being sigma x, A1 being sigma z. Okay, so this is, you know, measuring along x and z, right? X and z, and then you have the 45-degree one, right, which we write as B0 defined as sigma z plus sigma x, and B1 by root 2. B1 defined as sigma x minus sigma z by root. Okay, so these are the. So this is important to know because the goal here, I've not told you what the goal is, right? So this is just like the standard Bell things that we've already seen. So now the new thing, which is what we call self-testing, is the following statement informally. Okay, so the goal is to show that any state and measurement, okay, so we'll only do it for state for the moment, but you can also generalize it to measurement, that maximally violates beta CHSH, okay, is the same as phi plus, okay, up to local isometries. So this is what we'll try to prove today. Okay, so that's the main goal. So we just look at any realization that gives you the maximum violation, and we want to conclude what state they must have used, okay, which is a very powerful statement if you think about it. Okay. All right. So it's section 4.2 of the paper, whose title I haven't told you. I'll tell you later. Sorry. Right. So the key now, the key idea here is to show that suppose you do have such a maximal violation, then the observables being used, the anti-commutation on psi will vanish. B0, B1. Okay. So we'll first establish this, and then we'll see how this is used to show the statement that we want to show. Okay. So we'll build the isometry explicitly, but let's look at this part. Okay. So let me first tell you the general idea. So right now we're doing it for CHSH, right? We're doing it for a special kind of Bell inequality. This also holds much more generally for lots of different families of correlations. So in general, the strategy is as follows. So what you do is you use a sum of squares decomposition. So suppose that, you know, B is the Bell operator. So let B written as ABXY, WABXY, MAX tensor MBY be the Bell operator. So the Bell operator is an object of this form. So this thing would be a Bell operator in general. Okay. So this is the Bell operator. So I can quickly tell you in one word what we're doing. So we are doing self-testing. Yeah, do you know what that is? Have you? Okay. So it's very straightforward. The statement is very straightforward. It's difficult to prove, but the statement is the following. So suppose you have a Bell inequality, okay, and you're able to violate it using some state and some measurement. Okay. Basically, not only can you violate it, you also get the maximal violation. Okay. Then what we want to do is, just from that fact, we want to deduce what state you were using to do the violation. Okay. And what we'll show is that if you're doing a maximal violation, then there exist local isometries. So, you know, isometries that you apply on Alice's part separately and Bob's part separately, such that the resulting state is essentially the maximally entangled state, 5+. So that's the theorem we're trying to prove. Okay. So now that I'm saying it, I can also quickly say that the key step in doing this is to establish that the observables that you're using, they actually anti-commute on psi for both Alice and Bob. This is the technical thing that we're going to prove. Okay? And I was describing what's the general strategy for doing this. So suppose you write the Bell operator. So, this is a general Bell operator, and then the idea is that okay, and also you let beta q be the max quantum violation. Okay, max quantum value of beta. Right, max quantum value meaning using proper measurements and a state. Okay, so now the first note is that beta q identity minus the Bell operator B is positive semi-definite. Okay, why is that? Right, right, because the positivity. So if A is PSD, right, this is equivalent to saying that psi A psi is greater than 0 for all psi, correct? And then just by definition of beta q, we know that this is going to be always positive, right? Is that okay? Okay, the second note is, this is fine, right? Praneeth? Okay, okay. Yeah, I can never tell whether it's too slow for you guys or you guys are falling behind. I have no idea. Although I think you almost never fall behind, but okay. So now what we're going to do is, because it's a PSD matrix, so from linear algebra we know that you can write it as a sum of positive matrices, right? And this is a positive matrix just by construction. Okay. Okay. And then finally, the nice thing now is that if you have maximal violation. So suppose that psi gives maximal violation. Okay. Maximal violation or maximum value of B. Okay. Then it must be the case that beta q identity minus beta, B acting on psi is 0, right? Because by definition you got the maximum value, so it has to be 0. This essentially is equivalent to, by just using the sum of squares decomposition, this is equivalent to saying that psi acting on p dagger lambda p lambda psi is 0, right? Just by substitution, I've not done anything here. And this is equivalent to saying that the norm of p lambda psi is 0 for all lambda, right? Because you are summing positive numbers and the sum is 0, so each number has to be 0. And that in particular implies that p lambda of psi is 0. Okay. So starting from the maximal violation, which is a statement about probability amplitudes and so on, you're basically able to get a constraint on the operator itself. Okay. That p lambda, like you get a null vector. And it turns out that often you can use this psi. So psi will be the maximal violation state. So using psi and this, and the only property of psi we used was that it was giving the maximal value, right? So therefore using this you can actually get some strong constraints. But then you need to know a little bit more about what the inequality is to get more concrete state. But that's the general approach. So let's see how it applies to our case. Yeah. So you have to work with the Bell inequality that you have, and then so you have to do the sum of square for the specific Bell inequality you're thinking about. So it's just the approach. I'm not saying it's a general algorithm, but yeah, I don't actually. So there are results that say that essentially for any pure maximally entangled state you can find, for any pure bipartite entangled state, you can find a Bell inequality. You can self-test it basically by finding an appropriate Bell inequality and measurements. But yeah, that result is not. Yeah, we won't be able to cover it. I wanted to cover it, but too many things. Okay. So. Right. So now, how does this apply to our case? So for us, yeah, maybe let me just write it for the sake of completion. So now we're back to trying to establish B0, B1 vanish on psi. Okay. Yeah, I don't know why I'm sweating so much. Okay. So, right, so we're going to use essentially the same idea. Now we know beta q is 2 root 2, right? This you proved in your assignment, Sillson's bound, right? And then beta CHSH is just the inequality. And it turns out that one can write it as follows. So 1 by root 2, A0 plus A1 by root 2 Okay, so this is equation 30, and one can, okay, so this is one can verify. It's just a direct calculation. So verify using equation 20. Right? So equation 20 was saying that, you know, A dagger is A and A square is identity and things like this. Okay, so this we already saw. So you can write this specific decomposition, and it's a sum of squares, right? Like we said here, right? So we have a sum of squares decomposition, and so therefore, by essentially the same argument, for any psi such that psi beta, the Bell operator for CHSH psi is 2 root 2, it holds that A0 plus minus A1 by root 2 psi must be equal to B01 psi, right? So this has to be 0 and this has to be 0, right? So I've just written it in a single statement, but that's what it's saying. Okay, and this backslash notation or whatever, forward slash notation, this is forward slash, right? Or is this forward slash? I never know. Okay, whichever. So slash, just call it slash. So 0/1 is just plus minus. Okay. All right. Okay, and then what does that mean? So this in particular, so using this fact, one can show that B0 and B1 are going to anti-commute. Okay, so why is that? So we basically just substitute. So let's do that. So B0 B1 plus B1 B0, right? So this is just by definition of an by opening the anti-commutator, comma, sorry. Then A0 A1 using this. Okay, I'm ignoring the normalization. A0 plus A1 acting on B1 acting on psi. Right, there's a big bracket. I just substituted for B0 B1 from the expression, and then you can substitute again, and you'll get A0 minus A1, A0 plus A1 plus A0 plus A1, A0 minus A1, okay, psi, and this object vanishes because wherever you have opposite indices, you'll pick a negative sign relatively, right? Because as you know, A1 A0, this comes with a minus sign, and A1 A0 is going to come with a positive sign from here, and the other way, and the squares will cancel because A squares are identity. Okay, so you can check. This is not very difficult to check. Okay, and similarly, so proceeding exactly in the same way, right? Because these are essentially equivalent, right? Like they're symmetric relative to each other. They just at an angle. So whatever arguments you deduce about A, you can also deduce about B. Or sorry, whatever you deduce about B, you can also deduce about A. So similarly, you will get A0 A1, the anti-commutator of psi is 0. Is that okay? I'm just trying to show them self-testing. So yeah, so self-testing is the statement that if you have a maximal violation of Bell inequality, then, sorry, it's the third time I'm saying it for those of you here, but I think it just takes a minute. If you have a maximal violation of some Bell inequality, in this case we're looking at CHSH, then we'll prove that the state that you use to get the maximal violation is essentially the Bell state, and the notion of essentially is local isometries. Okay, this is what we're trying to prove, and the way we are doing it is by first looking at, we formalize the most general strategy as measuring observables A0, A1, B0, B1, and psi, and then just from the assumption that psi is maximally violating, we are trying to show that these things will anti-commute on psi. Okay, so this is what we established over there. So now we'll use this fact to construct such an isometry for any arbitrary state and show that the isometry actually results in this phi plus state. So that's the idea. Okay. All right, so now what we're going to do is we look at, so we now construct the isometry. Okay. So what I'll do is I'll first give you the construction, then we look at why this construction sort of might work, and then we'll prove that it works. So here's the construction. The construction is that you have ancillas, so you start them with A prime, B prime. Okay, so the isometry is basically, so isometries, you know what they are. They basically preserve angles, and they can potentially go to a larger subspace. Okay, because of course if you're going to a smaller subspace, you can't preserve all angles of the initial subspace. So you can potentially increase the subspace. And one way of modeling isometries is to just have unitaries, but fix some of the inputs. That would essentially correspond to an isometry on the remaining things. Right. Okay, so let's look at this. So we start with the Hadamard. Oh, sorry, I should have mentioned. So we are taking the system to be on AB, okay, and we want to extract the state onto A prime, B prime. Okay, so A prime, B prime will in general be 2-qubit registers. Single qubit registers. So A prime, B prime together are 2-qubit registers. A, B could be arbitrary. So we're not assuming what the dimension that is being used by the adversary is and so on. Right? Because we don't want to assume anything about the inner workings. We want to deduce this. So we start with applying Hadamard, and this is register AB. So here, this is where the state being used by the adversary goes. Okay. So given the state, what you're going to do is you're going to first apply Hadamards on these, and then you're going to do a control Z A and a ZB here. Control Hadamard again, and this is XB, XA, Hadamard, we're going to get some state psi here, and this state is what we're going to want to prove is going to be phi plus if this psi corresponds to maximally entangled state. Okay, so this is the isometry. Okay, so let's see why this might actually make sense. Why would someone write an object like this? Okay, so yeah, in general they're not. So in general they correspond to the observables used by, we'll write this explicitly actually, you're right, I haven't specified these explicitly yet, but they will be written in terms of the observables used by the adversary. Okay, yeah, so sorry, I hadn't fully specified what these are. Okay, so now let's build some intuition. Okay, so suppose the physical state, by physical state I would mean psi. Okay, we are essentially assuming all states are physical, but this is the unknown sort of state. But suppose for the moment that this state psi is a 2-qubit state. And XA, XB, ZA, ZB are just the Paulis. Okay, this is just to build intuition. This is not how we actually construct the isometry, but just for intuition. Sigma ZB. Okay, so suppose this is the case, and now the claim is the action of the circuit of phi basically is to swap psi with 0 0. So AB will get swapped with A prime B prime and vice versa. Okay, so let's actually do this because I think it's good to sort of check it once. So let's write it down. So you have 0. Suppose I write AB, right? So we'll extend the result by linearity. So let's just try to do it on AB. Hard mod ZA, ZB, hard mod, control, hard mod, control ZA. Oh, sorry, XA and XB. XB. And that's it, right? Okay. So the state here, right? Sorry, here there's also 0. Okay. And these are A, B. I'm not going to label them again. A prime, B prime. Sorry, label them throughout. So the state here one can write as plus AB plus. Right. This is elementary, so nothing complicated happening here. State here one can write as 0 plus minus 1 to the A1, right? AB. And then 0 plus minus 1 to the B1. Right, you're just applying a phase controlled on whether this was 0 or not. The state here becomes A B B, right? Because this is a plus or minus depending on whether A was 0 or 1. So if you apply hard mod, you'll go back to the computational basis, which is just encoding NB. And finally, the last step here will give you what? It will give you, now it's just control X, right? So if I do control X on this, what do I get? Just a sec, let me make some space. So you get the swap, right? Right? So you've swapped AB into the outer registers, right? Which is what I asserted here. So you had some state psi. It could be a linear combination. So I just took it to be AB, but you can extend it by linearity. So you started with AB, 0 on the outside, and then in the end you'll end up with zeros on the inside and AB on the outside. And note crucially that you unentangled it, right? Because if this was a superposition and you had left AB, then you would get like a mixed state, which is not what you want. So regardless of what AB you have, this will always be 0, granted you start with zeros here. Okay. So even if you have some entanglement here, it will get swapped into this. So why are we using such a convoluted way of building the isometry? The reason is that we want to use operators because we don't know the dimension of A and B, right? So you cannot use normal gates. So you want to use the measurement operators of the adversary directly to build the isometry, so that regardless of what dimension they're using, the properties of the maximal violation allow you to extract the appropriate state from whatever physical state they started with. Okay, so makes sense, right? Yeah. In this example, it is. In general, it's not. Yes.
Okay. In this example, it is.
Yeah. In this example, it was very, very explicit, right? I was just taking it to be a qubit, and I was taking Pauli matrices and so on. Otherwise.
Okay. But how do we do this swap when we don't know the dimension of AB, and like which qubit of psi AB do we even swap to?
Right. Exactly. That's a very good point. So here we are thinking about qubits because we're using Pauli matrices directly, but we'll not use Pauli matrices. We'll use the fact that those observables are anti-commuting and then work at that level. So it could be that the adversary is encoding 2 qubits in a very high dimensional space in some way, but the relevant qubit part we'll be able to extract because the measurements are binary, right? So we will be able to use the anti-commutation. So it's obviously not trivial, right? I mean, I'm just giving you some intuition. I don't know how they came up with it. This is like, genius people. Some of you might find it easy, but for me certainly it's not. Okay, so now the hope is right. So the hope is that this action is preserved. Action is preserved for arbitrary psi and appropriate choice of x a b z a b, right?
Is this related to the Jordan decomposition when you define the qubits, that you just find the properties and
I think one can do it through Jordan as well. I think here it's done in a slightly different way. I think there are many ways of doing it. But yeah, I'm guessing wherever there are two outcome thingies, Jordan does show up. So maybe it does in some way. But
yeah, because Thomas Lecton defines qubit in this way without saying that they are polymatrices.
right, exactly. Yeah, I'm sure it shows up for the. Yeah, so I think when you want to prove it for arbitrary, so here I'm trying to do the maximally entangled state, but I think when you're trying to do for, you're trying to establish the general result that any pure entangled state will admit such a self-testing result, I think that you have to use Jordan's decomposition, right? So let us define so let us fix the choices of these observables. So what we are going to use is A0 and A1. XA would be 1 by square root of 2, A0 minus A1. ZB would be B0, and XB would be B1. Okay, so that's the definition that we are using. Why this definition will slowly become clear, hopefully. Okay, so the first thing is that.
Sorry, and these operators are known to the verifier? Whoever is the
Yeah, so we are trying to do an existence proof. Because we want to say that whatever you're using is up to isometries equivalent. So I'm not obliged to find the isometries. I just want to say that they exist, so that they're equivalent. Yeah. But that's a different question. Yeah, I don't know. Maybe it's worth looking at separately whether in what cases you can efficiently.
So I can think that this ZA, X are not known, but if they were known, then you will show something.
Yeah. Exactly. So whatever if I had access to the adversary, and I could suppose in just a black box way, if I could control the operators being used, like control as in control not control, then it would be enough to build the isometry exactly like it has been written there. Okay. Oh well, the linear combination. This actually requires a little bit of algorithms like stuff to do, because you're doing like linear combinations of operators, so you have to do a little bit of work. But okay. Any more questions? Is everything good? Okay. So now so ZAXA is 0. This is essentially by construction. Okay, and the reason is that you just expand it. So you put ZA as A0 plus A1. XA is A0 minus A1. Right, plus the other way, A0 minus A1, A0 plus A1. But this is very similar to the expression we saw, right, that it squares and the opposite indices end up with opposite signs, right, so it vanishes. So this thing is 0. Okay. The second note is that ZBXB vanishes on psi. Okay. So this was true at the level of operators, right? Now this is true on the support of psi. Okay, and why this is because we established this, right? So we established that B0 B1, the anti-commutator on psi, vanishes. This we did using the sum of squares just a few minutes ago, right? So this is where it's being used. Okay, and the final note is that ZA acting on psi is ZB on psi, and XA on psi is xb on psi. And yeah, this is coming from okay. So this we also showed, right? We actually use this to prove this result, right? So we know this is true, and this is just by definition because you look b0, b1. So z sub b is, for example, b0. So you put b0 here, and then za is a0 plus a1, a0 plus a1, right? So it's just written in different variables, but this is exactly the same statement. Okay. So I'm going to keep the isometry here because it's, or maybe I keep this one. Yeah, we'll draw it again, it's okay. All right, and okay, so there's a little bit of a subtlety, so let me explain that before we move on. And I also did not do, I forgot to complete the proof, so there's a small statement that we'll take on faith for today. It's in the appendix. So the issue is the following. So to ensure that phi is an isometry, so remember what I was saying, right, that if everything is unitary and you just fix these two guys, then it's an isometry on this part, right? So that part is fine, but somehow you have to make sure that this is actually unitary, and that may not be for general z's. Okay, so what do we need? So let me be a little bit more explicit. So to ensure that this is an isometry, it suffices that za xa, zb xb are unitaries. Now zb and xb are unitaries. Zb xb, right? This is just because of the definition of how we define them. We define them in terms of these POVMs and their additions, and they satisfied b dagger b. It was Hermitian, and then we had b dagger b being identity because b square was identity, and this was because this was like a sum of projectors which was spanning the entire space, right? So we sort of established this part. But now if you have some combination, then it's not clear whether this would be the case or not. And actually in general it's not the case that they are unitaries. So za and xa may not be unitary. And the way they fix it, this issue, the solution is to what they call regularize. Okay, so regularization is the following thing. It's a very physicsy thing to do, right? To regularize things that don't work. Okay, so you replace z with z tilde, where z tilde is defined to be just z, but with 0 eigenvalues replaced with 1. Okay, so the main issue is that of course z could have 0 eigenvalues, right? That's when it becomes non-invertible. So what they do is they just define z tilde, which is the same as z, but you remove the 0 eigenvalues, and then you define z hat to be the normalized version of z tilde. Okay, and the claim that I won't be able to prove is that doing this does not change the action of z on psi. So z hat on psi happens to behave exactly like z behaves on psi. Okay, so this is the statement that is proved in the appendix, which I forgot to prepare for this lecture. It's an appendix A.2. Okay, so it's just a subtlety. For the moment, we'll just assume that z is unitary. Okay, for our purposes, but under the hood, what is happening is we are replacing z with z hat, and all the properties that we're using are basically the action of z hat on psi, right? That's how we're doing. So it's going to work.
So this will be minus half z and psi?
Minus half? Normalization. Yeah, but when you do the normalization, you'll have z dagger to be identity, so you'll also have squares from here, and it'll work. I had the same doubt. So. Oh.
I think it's true because psi maximizes psi is
Yeah, so it couldn't be a null vector, probably. Is that what you're saying?
so psi is the one that maximizes the del inequality.
Uh-huh.
So z psi will correspond to the maximum eigenvalue of z.
Yeah, I mean, these are like sums of different things. I'm not sure if maybe it's something like this. Yeah, I haven't checked. Yeah, but it has to do with, obviously it has to do with things being extremal somehow, and I think in particular it might suffice to show that psi is not a zero eigenvector, right? Because everything that part is not changing. So I think that might be easier to establish somehow. I don't know. Let's think.
Also, is this true for all states psi, or is it only for
In our construction, yeah. I don't think it's true for. In general, maybe this regularization doesn't work. I think for CHSH it works, but I don't know if it works in general. Yeah. Okay. All right. So now we're essentially on the last 2 pages. Not bad. Do I want to keep this? Yeah, let's keep this. Let's keep the definitions. Okay, so I'll remove this subtlety part. That's not really. Okay. So now our convention is just that we'll simply assume x, a, z, a are also unitary. All right. So now the first thing we're going to note is that the action of psi, action of phi on psi for some general psi using these variables, these observables for constructing the z and x gates would be as follows. Identity plus ZA, identity plus ZB, acting on psi. This part is a little bit algebraic, okay, so you have to be patient. And you have to follow along, otherwise it will be very boring. Okay, so 0, 1, tensor identity plus ZA, XB, identity minus ZB, psi. Okay, can you guys guess the next one? Given this, what would be 1, 0? Okay, yeah, I couldn't have guessed it. So, well, XA comes first, then you have identity minus ZA, like you were saying, and this one becomes plus. Okay, and what about the last one? 1, 1. Do you see 2 x's? Right, because this one was adding xp, this one is adding xa. So when they're both 1, you potentially add xa, something xp, right? Sort of looks reasonable if you had to guess.
This is the circuit you are writing, right?
There's the result of applying the circuit. Yeah.
That circuit on the left.
Yes, exactly. Okay, so 0, 1 seems to be controlling whether or not you add an x, and it also seems to be controlling whether you get a minus sign on the z, right? Okay, but we can actually do it more explicitly. That way we'll have some handle on what's going on. I'll not do the full calculation. I'll do it enough so you are sort of convinced that it makes sense and that we're not cheating. Okay, so the state at step 1 will be what? So I'm just writing these two A prime B prime systems I'm writing first, just as they are writing, right? So these are, sorry, I should write A prime, B prime, and this is of course AB, right? So in the same notation, so at step 1 we'll have 0 plus 1. I'm not writing the normalization, okay? So 0 plus 1 psi. This is fine. It's just the first step. Just apply the Hadamard. The second step, we have to apply a control Z depending on the first qubit, right? So this becomes for 0 0 it does nothing. For 0 1 it applies Z, okay, on psi. 1 0 it applies Z tensor identity on psi, and then for 1 1 it does what? Yeah? Okay. For the third one, so for the third step, what do we have to do now? We just have to add a Hadamard, right? So we basically, so this part is going to be a bit tedious, but let me write it out, okay? So I'll write down the first 2 or 3. So let's do this. So 0 plus 1, 0 plus 1, acting on psi, okay? Then 0 plus 1, 0 minus 1, right? Because it's 1, you apply Hadamard, and now you have identity tensor Z here. So, okay, and similarly you'll have Z tensor identity and Z tensor Z, right? So those are the terms you'll get. All right. So okay. So now let me write the fourth one. So the fourth one is I'm going to apply control X, and control X on this one. Right. So let's write it down. So 0 0. I'm writing this term and just collecting the control registers. Okay. So you get 0 0 acting on psi plus 0 1 acting on identity tensor X, right? Because 1 tells you apply X, plus 1 0 does X tensor identity on psi. Actually, maybe I can drop writing psi every time. I'm so stupid. Okay, yeah, let's not write psi every time. Sorry. Okay, so 0 1 is identity tensor X. Okay, there's a psi. I'm not writing the psi. And then plus 1 0 is going to be X tensor identity, and then plus 1 1 is X tensor X, right? That's this part. So this part. Okay. The next one we'll have 0 0, but this is it already has an identity tensor Z, even without doing anything. When you have minus 0 1, you'll have identity tensor XZ. Okay, and then plus 1 0, you'll have X tensor Z, and then plus 1 1, you'll have X tensor XZ, and so on. So then you can start to see what's going on, right? You can start to see that for 0 0, right, you're collecting, the identity is coming from here. There'll be like one full identity, then there's identity tensor Z, one of them's come from, and the other one, and then the x's get added, right? Every time you have a 1, you accordingly add x at that location, so they squeeze it in the middle if it's in the second. If it's 1, then you put it in the beginning, and so on. Okay, so it should at least be plausible. I mean, it's just calculation, but just to make sure that nothing looks mysterious. Okay. Now comes the next bit of rewriting. So maybe I will. What do I want to erase? Okay, let's just erase the calculation. That's not very illuminating, besides making this less mysterious. Okay. Okay, so I hope you believe that this is true. And then the next note. Okay. Then the next note is that you can actually simplify this. Once you write it like that, you can write it as sum over ij 0 1 ij, okay, tensor. So this is on A prime B prime. F hat ij psi AB, okay, where F hat for F hat ij defined as follows. So f hat ij is a quarter xi to the a, identity plus minus 1 to the I, za, xb to the j, identity plus minus 1 to the j, zb. Is this fine? Just a rewriting, right? Like we already saw that you're adding the sign and the x's depending on the indices. So that's what I've captured over here. Okay, and then now let's reason about this. So using 35, which basically just said that za on psi is the same as zb on psi, and xa on psi is the same as xb on psi. Okay, one can conclude that identity plus minus za, identity minus plus zb on psi is 0. Okay, so why is that? So you can expand this. So let's expand it. So the expansion would be identity minus plus zb plus minus za plus za zb. Okay, and we already saw this, right? So we already have za, the action of za on psi and zb on psi is identical. So these two terms have the opposite sign, they'll vanish. Right, that's fine. So they will cancel on psi, right? And za zb, so this is, so these are unitary, right? So unitary and Hermitian. So I can left multiply with za, and this will be psi is equal to za zb, right? So which basically means as far as psi is concerned, this is identity.
The minus sign, yeah.
With the minus sign, and this will cancel.
The minus sign will come before, right?
I messed up a minus, is it? Yeah, sorry, there's a minus here, right?
And that is the plus sign.
Okay, so this will cancel, so this vanishes. So what does this tell us? This tells us that, you know, so how do you get opposite signs here? You get them by using either 0 1 or 1 0, right? That's how you get opposite signs. So basically what this means is that f hat, so this implies f hat 0 1 on psi is the same as f hat 1 0 on psi, which is 0, right? This is fine? Okay, and yeah, let's remove this part now. And the last step for us now is to establish that f hat 1 1 psi is basically, so this is claim, we'll just show it in a second, f hat 0 0 psi. Okay, and how do you see this? So you basically substitute. So for 1 1 we're going to have xa, right, and identity minus za, xb identity minus zb on psi, right? Just by definition, not done anything. And now you can see where the commutation relations would appear, right? Anti-commutation, sorry. So this becomes plus za acting on xa and identity plus zb acting on xb psi, right? And this is because we showed, because of the anti-commutation relations, right? So we showed that xa and za anti-commute and xb and zb anti-commute with their support on psi, right? No? Okay. And then finally you get from 35, which was, so so we use the fact that za psi is the same as zb psi, xa psi is the same as xb psi, Okay, plus ZA identity plus ZB. Right. So XA and ZB act on different systems. So you can commute them past, and then XA XB, because of the unitarity of XA XB, this will vanish. So you'll get this last term. Right. Good. Okay. And what is this? Well, this is just f hat 0 0, right? Because no sign, no x's. That's what 0 0 corresponds to, just from here. So this is f 0 0 acting on psi. Okay, so what does that mean? That it means that f hat 0 0. Oh yeah, I already wrote it. So f hat 0 0 and f hat 1 1, they are identical. The cross terms disappear. And what was this? The subscript encoding? It was encoding the state here, right, on the extracted qubits. So basically, what this means is that, so the conclusion is that you end up with this. So you apply the isometry on psi AB, okay, and you'll end up with the maximally entangled state tensored with psi, okay, where this is f hat 0 0, some normalization on psi, and this part is just 0 0 plus 1 1. Okay, magic. So there's lots of extensions of this result. People have looked at how to make it robust. So for example, at the moment we looked at the case where you have exact maximal violation, but in practice obviously you'll never have exact maximal violation, you'll always have some small error. So people have looked at how to quantify it. So instead of saying that you'll exactly have this state, they're like, it'll be close in some notion of distance, trace distance, fidelity, whatever. To this state, people have looked at, so far we just looked at how to do the state itself, right? We didn't see how to do the measurements, but one can also extend it to the measurements themselves. So one can show that the measurements are also essentially up to some isometry, the same as Pauli's, and so on. And finally, people have also looked at, so there is some subtlety with the sigma y measurement. So when you do the measurements, you can show that x's go to x's and z's go to z, and then xz you can call sigma y, but there are some subtleties over there. So that is a separate piece of work. And then the final extension is where people have shown that, like I already said, that it's not just true for the Bell, the Bell case. I'm saying the maximally entangled state, you can essentially do it for any pure bipartite state, and so on. So there's lots of work in this direction. And it would be useful for us because at some point we would want to do verification of BQP, and being able to certify that without, by just classically communicating with the adversary, we would be able to certify what kind of measurements the adversary is making, whether we want them to make a Hadamard measurement or a standard basis measurement, which is Z and X. So that would be a very powerful tool. Hopefully we'll look at it at least a little bit in the next lecture. And
so what is the reference for this self-esteem?
I'll send it to you. I forget the name of I just printed it from in between, sorry, but I'll send it to you. And yeah, there was one more small thing I wanted to mention. Okay, I can't recall, but when I do, I'll mention it. Okay, so that was the self-testing part. Yeah, we're in between topics. It's a little bit hard. In the remaining time, I wanted to at least finish the what was it? The existence of PRUs. So I'm going to try to do that. Oh, Yeah, so the English word, right? So I might be slightly wrong, but in my head, self-test was that the correlation is testing itself, like the bell pair can test itself essentially. So you just look at the correlation, and that itself gives you a guarantee that it is a bell pair. So you don't have to construct any new test, like the very thing that you use to the very correlations that produce the bell whatever. Yeah, the very correlations that arise from the bell state are also enough to certify that it is a bell state. So the correlations can self-test themselves. I don't know if it's the best answer, but or another way mathematically, although it's called rigidity, where you have some notion of uniqueness, and it's also robust. So then I think it's called rigidity, that you have some solution and it stays essentially it's unique, and even up to some small error it stays unique. From any state, if you can extract a bell state, yeah, I mean then it's immediate, no? Because if you have some isometry that you're applying to get the bell state, so you apply the isometry and then you do the bell measurements, and the usual measurements that you do for the bell case. So then you'll immediately have a violation. So that direction is relatively simple, no? No? Am I misunderstanding? No. I mean, I thought you're just saying this, right? I thought you're saying that if you start with, like, suppose I have some state psi, right? And I apply some, say, SA tensor SB, like two isometries, right? And they produce, say, the bell state phi on A prime, B prime. So suppose this goes from A to A prime, and this goes from B to B prime. Right? They're isometries, right? So they're increasing the size of the space. So you have some isometry which does this, and then you don't know, it does something else to the rest. So let's just call it junk, AB. Right? So you don't know. Like in this case, it was some state that was produced. So if it does this, then this object, once you have access to this, then you can just use it as a bell state, right? Like then you can apply the usual measurements that you do for the bell case. So you will obviously, just from the fact that bell violates the maximally entangled state maximally violates the bell inequality, your state will also immediately violate it. Right? And the way you construct the measurements would be like, suppose you were using say sigma x, right? Sigma x for one of the measurements, then you would just make whatever the, well, okay. Yeah, to get the measurements, you may have to, yeah, you may have to purify things a bit. Okay. So you may have to purify the isometry to do it. So if you have like a unitary, then you could, so my problem is the following, right? So if you had some observable law that you were measuring on psi AB, and this was acting on, say, A and tensor identity, right? So I could always do this, right? I could always do conjugate it with the unitary, right? But since it's an isometry, this conjugation is a little bit more tricky. So the easiest thing is to just expand the isometry to being a unitary, and then you can apply this, and then this thing would be your new measurement, and this is your the correct state that you want to apply it to. Or actually, am I saying something wrong? Yeah, you could just apply the isometry to the state. Actually, it's probably okay. Yeah, so the correct measurement would just be to apply this isometry to the observable and use your original observable, and it will work. Yeah. Sorry, yeah, I got confused slightly. Okay, so if you had psi and some m's that you were using, say MA for Alice and MB for Bob, and you knew there existed this isometry, you would just do SA of M. Sorry. If these were like the, sigma x, for example, and sigma z, whatever, for the original Bell inequality, then you just apply the isometry to this, and this will give you the, the measurement that you want to make on your case. So once you have the isometry, it's relatively straightforward. Okay. Okay, so now my objective would be to finish the PIU stuff. So at least we complete that, and in the next lecture as well, we'll continue with it. And verification, I think I'll just have to record. Like we can have some extra lectures later after your exams or whatever, and we can see how to do verification. If we don't have enough time, okay. Okay, now the problem is I forgot to what extent. How much had we done, do you guys remember, for the pseudorandom unitaries? Does anyone remember? Nobody takes notes anymore, do you guys? No, okay. Oh, this is not good. Okay, pseudorandom unitaries. So let me write the formal statements at least, and then we'll see if we saw the proofs or not. I think I wrote the formal statement, we just didn't do the proof. Right, I think I just argued that it's like Drover's search, but I didn't do the proof. Okay, so let me write the lemma. Okay, so it said consider a, yeah, maybe one thing I should say is that, let me write it from the beginning. I think otherwise it would be a bit confusing. Okay. So the PIU ensemble that we're going to use is that for a given length n, the PIU ensemble is uniform over the 2 to the n different n qubit unitaries in UN. Okay, so that's the ensemble. And UN, do you guys remember? This was like the direct sum of exponentially many n qubit unitaries, right? And then we were concerned about the efficiency, and then we said you could like think of it as a control for deciding which unitary you want to look at and so on. Okay, so that was the definition, and the notation was, we'll use u sub k for a fixed n. Okay, so that's the ensemble, and our approach was that we first established that average advantage of polytime adversary is small. So advantage meaning distinguishing this from Haar random. Okay, so we'll establish this on average, and then we'll strengthen it to the situation that we want. Okay, so the lemma says that consider a quantum algorithm O, U, actually the U is normal, that makes capital T queries to U. So U is U1 to UN in UD to capital N, okay, and this unitary is UD. Sorry, this O is some unitary in UD. Okay. So you're given so this algorithm is given access to this capital N many unitaries and then one other unitary. Okay, and remember capital N is exponential in it's 2 to the n. Okay. And then we had that for a fixed u, so we define advantage of a to the u as probability you sample k uniformly at random from the exponentially many options you have from 1 to n. You give it access to u sub k. So you basically pick one of these unitaries at random and give that as the first oracle, and then you give access to the second and you call this 1, and from this you subtract the probability that O is sampled uniformly at random. So O is basically a high random unitary. No. Okay. This is what is termed the advantage. Okay. So the statement says that this advantage, so then there exists a constant c greater than 0 such that on average this advantage on a to the u is at most ct square by capital N. Okay. And the intuition for the proof which I gave you last time was that, so I'll not write the intuition this time, I'll just verbally say it. The intuition is that what you're basically given intuitively is that you're given one element out of these, right? And in the other case you're not given, you know, it's not in the list. And so basically you have to find it's like Grover search, whether or not there's a marked element in the set. Okay, so you can essentially reduce it to Grover's. That's the intuition. So that's what we'll do now. We'll try to actually formally give the proof in the last few minutes. Okay, so here's the construction. The construction is that you have b to the x, which queries a string x in 0, 1, capital N, as follows. Okay, so b draws a unitary v0 to vn from the set of all unitaries, capital N plus 1, from mu d capital N plus 1. Okay, this is fine. And now, so okay, so you're sampling one more, right? So you starting with v0. So there's capital N plus 1 elements, and then b does the following. So b runs a, replacing queries to O by those to V0. And queries to, so this is 1, and queries to U sub k in U by V0 if x sub k is 1 and Vk if x sub k is 0. Okay, so we are using A to construct a new algorithm B, and what this algorithm is doing is that whenever so A could query both, right? It could query either O, right? Where is it? It could either query O or it could query U. So what we are saying is that whenever it queries O, this A algorithm, this B algorithm is going to give it responses from V0, and whenever the query is made to U sub k, you basically check whether x sub k is 1 or not, right? Because x is a capital N bit string. So you check whether x sub k is 0 or 1, and you output v sub 0 or v sub k accordingly. Okay. All right. So now we let E sub k to be the indicator vector. So basically so this is 1 wherever you have k equals 1 and it's 0. So it's basically like this, right? So it's zeros everywhere, 1 zeros. So this is at the kth position. Okay, so that's the string E sub k. Okay. All right. So the first note is that you sample u from this distribution mu sub mu n, right? So that's the set of capital N direct sums of random unitaries. And this advantage we're going to write as follows. So this advantage for the algorithm A can be written as, just from the definition, that n by linearity of expectation as follows. So u sub k comma u equals 1 minus expectation u sample from mu sub t, probability, oh man, my O and 0 look essentially the same, I'm sorry for that, O and u equals 1. Okay, so far I've done nothing, I've just substituted the definition of advantage with this expectation. And now comes the interesting observation, because so this apparently you can write as probability that you sample k. Okay, so this is the step that will take a few seconds to convince yourself is correct. E sub k is 1 minus probability, you're given 0. Okay. So clearly this case, right, where this O and U are independent, right, this is exactly the same as this case, because you see B is going to always substitute O with V0, so that's an independent unitary, hard random unitary, and these remaining ones, because xk is always 0, right, so it's always using these remaining ones. Okay, so that's exactly the setup that we had here, sorry, here, right, that O is sampled independently and U are independent. There's no correlation between O and U. So this corresponds to exactly the case where B is given a 0 to the capital N. Yeah? Is that okay? And then B with E sub k is doing what? It's basically, so if you look at this, what is this saying? That you have a list of unitaries U1 to U capital N, and the kth one is the same as the one that was outside, right? And if you look carefully here, what is this one doing? So here you're going to, suppose your indicator variable was, like this, right? So this is the kth spot, right? So it was going to give you, it would give you V's, right? It would give you V's everywhere. V1 all the way to whatever, Vk minus 1, it will give you V0 and then Vk plus 1 and so on, right? V capital N, correct? And the first one was what? What was the first oracle to A that was given? V0, yeah? So this is how it's running A, right? In this case, this is what is being run by B, correct? Because it just substituted the, if you look at this, right? So 1 appears at the kth location, it substituted that with V0, right? Everything else is V1 to V capital N, and the first one is V0 just by definition of V0. But this is exactly what this guy was doing, right? Because here you were substituting, you were picking U sub k to be the first, right? Okay, I'll give you a second to convince yourself that these two are identical. Any doubt? Does it make sense? Okay, I'll wait a second. Just look at the definitions of B and A, and it should be okay. Oh shoot, it's time. Okay.
Is also gone.
Yeah, because this sampling is being done by B directly, right? So B is sampling this. So B is sampling in the first step. The same thing. Okay. So, and what is this? This is basically like just like the marked element, like, right? So these two oracles are identical, right? Except at one location, and you're making T queries. So we know from the the theorem that we've seen many times that the maximum advantage is going to be proportional to T square by the number of locations. Okay. So this is what we asserted, right? That the advantage on average is going to be at most this much. Okay. So in the following lecture we'll continue and strengthen things. Okay. Sorry, it went on slightly longer. I kind of lost track of time. Thank you.